Alright, Dalton's law of partial pressures. Dalton's law of partial pressures states that in a mixture of gases that do not react chemically, it is the total pressure, or equal to the sum of the partial pressures of each individual gas. So, my pressure total is going to equal all of the partial pressures, I guess, all added together. Okay, so we're going to do an example of one of these sorts of calculations. So for example, we have two gases are pumped into a 32-liter reaction vessel at 25 degrees Celsius, one after another. First, we have 6.2 moles of oxygen gas is pumped in first. Then, 8.3 moles of hydrogen gas is pumped in. So what would be the pressure gauge reading be after each gas is pumped in? Well, we have here our oxygen gas is equal to, so this is the information for the oxygen gas. This is what I know about my oxygen gas, and what I need to figure out is, again, my pressure, okay? And that's what I would love to see there, is what is the pressure, okay? Pressure is what I don't know. Now I have my equation, PV equals nRT, substitution, and I've solved now for the pressure. So now this is saying that therefore the first reading is 408 kilopascals before I add in my hydrogen gas, okay? Now, as I add in my hydrogen gas, we're looking at 6.2 moles plus 8.3 moles, okay? This is giving me 14.5 moles, okay? My temperature, again. Now, the question is, why am I doing this? Well, I need to know, why am I adding the moles together? Well, I need to know how many particles is in there. That's the most important thing there. There's 14.5 moles of particles. That many thousands upon thousands upon thousands of particles is in that chamber, okay? My volume is 32 liters. Again, I still have the same thing. Now, what I would love to see again is the fact that I'm solving for P. That's what I don't know. My pressure is what I'm trying to find out. Here's my formula, substitution, okay? Again, we're adding in, when we're looking at the number of moles in our calculation, this is the number of moles of the two gases put together, the number of moles that will be in there in the end, and the pressure that I'm using is what I'm trying to find out, okay? Now, here we go. Here's my end pressure, okay? And the second reading is going to be 1.12 times 10 to 30 kilopascals. Now, you can do it this way, totally fine. Or, you can calculate the pressure of the oxygen and then the pressure of the hydrogen separately and add the pressures together. It gives you the same answer. So, it follows Dalton's law of partial pressures, and I hope that you give it a try in order to figure it out. Quickly though, we have the ideal gases and real gases. So for ideal gases, we assume that there are no intermolecular attractions between the molecules of the gas. In real gases, however, there are attractions between the molecules. So we don't have to worry about considering this in our calculations because it is standard pressure and temperature conditions. The molecules are very far apart and are moving very quickly. Therefore, they do not interact much with each other. Real gases behave like ideal gases at high temperatures and low pressures, okay? Real gases, though, deviate from the ideal gas behavior at very low temperatures, so when the particles are moving very slowly, and at very high pressures, where the molecules are very close together, okay? Here's some information that you guys should know. Okay, I would suggest that you all write it down. And as a review assignment, you guys have page 156, questions 1 through 25, omitting question 12, 21, and 24. Alright, thanks very much. This is the last video of this section.